This is Mercury. Imagine standing on a world where the sun rises, pauses, reverses direction, and then rises again. Where noon can last for weeks. Where the ground beneath your feet is slowly splitting apart because the entire planet is shrinking. And where, despite being the closest planet to the sun, there are regions that have never seen a single ray of sunlight. Not once. Not in 4.5 billion years. For decades we thought we understood Mercury. A small, lifeless, crater-covered rock baking in constant sunlight. A leftover. A footnote in the solar system. But then we sent spacecraft to study it up close. And what they found didn't just surprise scientists. It forced them to rethink nearly everything they believed about how this planet formed, what it's made of, and whether it's actually inactive at all. It turns out Mercury is one of the strangest and most extreme worlds in the solar system, and we're only beginning to understand just how wrong we were. Let's start with the simplest question. How hot does it get? The answer is brutal. During the day, surface temperatures can climb to around 430 degrees Celsius. That's hot enough to melt lead, hot enough to melt zinc and tin, and in some cases, hot enough for surfaces to faintly glow. But here's the twist. At night, temperatures drop to about -180 degrees Celsius. That's a difference of more than 600 degrees, the most extreme temperature swing of any planet in the solar system. For comparison, most places on Earth only see a difference of about 10 to 15 degrees between day and night. So why is Mercury like this? Two main reasons. First, Mercury has almost no atmosphere. What it does have is something called an exosphere, a thin scattering of atoms so sparse they barely interact. There's nothing to trap heat, nothing to circulate it, and nothing to slow down the cooling process when the sun sets. The heat simply escapes into space. It's like removing a blanket in the middle of winter, except Mercury never had one to begin with. The second reason is even more unusual. Mercury doesn't rotate the way most people expect. Because it's so close to the sun, many assumed it must be tidally locked, always showing the same side like the moon does to Earth. For over 100 years, astronomers believed exactly that. But in 1965, radar observations from the Arecibo telescope revealed something completely different. Mercury isn't locked in a 1-to-1 resonance. It's in a 3-to-2 resonance. It rotates 3 times on its axis for every 2 orbits around the sun. This creates a bizarre consequence. A single solar day on Mercury, from one sunrise to the next, lasts about 176 Earth days. That's longer than 2 full Mercury years. One day is literally longer than 2 years. And because Mercury's orbit is stretched into an ellipse rather than a perfect circle, something even stranger happens near perihelion, its closest point to the sun. At that moment, Mercury's orbital speed temporarily becomes faster than its rotation. From certain locations on the surface, the sun appears to rise in the east. Slow down. Stop. Move backward toward the horizon, then stop again, and resume rising. A double sunrise. It sounds impossible, but it's real. And it's just physics. But Mercury's strangeness goes much deeper than its rotation. If you could cut the planet open and look inside, you'd find something that doesn't quite make sense. Its iron core makes up about 85% of the planet's radius and roughly 70% of its total mass. For comparison, Earth's core makes up only about 15% of its volume. Mercury is essentially a massive metal sphere wrapped in a thin, rocky shell. Its crust and mantle combined are only about 400 kilometers thick, less than the distance from New York to Washington, D.C. So, how does a planet end up like that? For decades, scientists believed they had an answer. Early in the solar system's history, a massive collision, possibly with an object close to the size of Earth, struck a young Mercury and stripped away most of its outer layers. The rocky mantle was blasted into space, leaving behind a dense iron core with only a thin shell remaining. This idea helped explain large impact features like the Caloris Basin, one of the biggest impact structures in the solar system. It made sense, but it might not be correct. When NASA's Messenger spacecraft entered orbit around Mercury in 2011, the first mission to ever do so, it changed everything. Before that, the only mission to visit Mercury was Mariner 10, which performed 3 flybys in the 1970s and mapped less than half the surface. Messenger stayed for more than 4 years, collecting hundreds of thousands of images and vast amounts of data before crashing into the planet in 2015. And what it found created a major problem. Mercury's surface is rich in volatile elements: potassium, sodium, sulfur, and chlorine. These are elements that should not survive extreme heat. If Mercury had experienced a massive, high-energy impact strong enough to strip away its mantle, those elements should have been completely vaporized. They shouldn't be there, and yet they are. That leaves scientists with a puzzle. How do you get a planet with such a massive iron core and thin crust, while still preserving volatile materials that should have been destroyed? Some researchers suggest Mercury may have formed farther from the Sun, in a cooler region, and later migrated inward. Others propose that comets or volatile-rich asteroids delivered these materials after the impact. More recent models suggest a grazing hit-and-run collision, one that removed much of the mantle without completely erasing volatile elements. Simulations show this could match Mercury's current properties surprisingly well. But even that explanation isn't perfect. The truth is, we still don't fully understand how Mercury formed, and that uncertainty is part of what makes it so compelling. But Messenger didn't just change our understanding of Mercury's origin. It revealed that the planet is still active today. Mercury is shrinking. As its interior cools over time, its core contracts. And as the core contracts, the surface has to adjust. The crust buckles, fractures, and folds. This creates massive cliff-like structures known as lobate scarps, giant faults where one section of crust has been pushed over another. Some of these features stretch for more than 1,000 kilometers. One of the largest, Enterprise Rupi, cuts directly across a major impact crater, meaning it formed after the crater itself. Over billions of years, scientists estimate Mercury has shrunk by about 7 kilometers in diameter. Think of it like a drying fruit. As the inside contracts, the outer layer wrinkles. Except on Mercury, those wrinkles are cliffs that can rise more than 1 kilometer high. For a long time, scientists believed this process had ended billions of years ago, that Mercury was geologically dead. But Messenger's final low-altitude passes revealed something unexpected. Small, fresh-looking scarps and narrow troughs, called grabens, that appear far too young to be ancient. Some may be as recent as 300 million years old. On a geological timescale, that's extremely recent. Mercury isn't just shrinking, it's still shrinking. And that likely means seismic activity, Mercury quakes, are still occurring today. Then there are the hollows, thousands of shallow, rimless depressions scattered across the surface, often found inside impact craters. They're bright, reflective, and completely unlike anything else in the solar system. They appear to be geologically young and possibly still forming. The leading explanation is that volatile materials trapped beneath the surface are being vaporized by intense solar radiation and solar wind. Without an atmosphere to protect it, the surface essentially breaks down as these materials escape. The ground collapses, leaving behind these hollowed-out features. It's as if Mercury's surface is slowly dissolving from within. And then there's its magnetic field. Mercury is the only rocky planet besides Earth that has a global magnetic field. For a planet this small, that's unexpected. Its core should have cooled and solidified long ago. But it hasn't. MESSENGER confirmed that Mercury still has a liquid outer core, generating a magnetic field. But even that comes with a twist. The field isn't centered, it's shifted significantly toward the north. No other planet has a magnetic field like this. This means the southern hemisphere is more exposed to the solar wind, which may have gradually altered its surface over billions of years. So this isn't a dead world. It's a planet that is contracting, cracking, outgassing, chemically evolving, and still active today. And we've barely explored it. Only 2 missions have ever visited Mercury. That's about to change. The Bepi-Colombo mission, launched in 2018, is currently making its way toward Mercury using a series of gravity assists from Earth, Venus, and Mercury itself. By late 2026, it's expected to enter orbit. Once there, it will begin studying the planet in far greater detail than ever before. It will analyze the surface, probe the interior, map volatile elements, and study the magnetic field with unprecedented precision. It may even detect changes happening in real time. Mercury is a world of extremes, the hottest and the coldest, the smallest, yet one of the densest. A planet where a single day lasts longer than its year, where the surface is still breaking apart, and where ice exists in shadows that sunlight has never reached. For a long time, we thought it was simple. We were wrong. The more we learn, the stranger it becomes. And that's exactly what makes it worth exploring. Thanks for watching, and I'll see you in the next one.